Hello to those watching this on the computer. I'm David, the Study Centre Coordinator at Uni of Adelaide, and this is Semester 1, 2025, and this is a revision seminar for Differential Equations for Engineers, the last version of this course before the new university is created, so yay, I guess. Interesting times. Okay. So I've been given some requests, and my first request was to talk about isoclines and nullclines. And according to the notes, these only happen when you've got what they call autonomous differential equations. So and an autonomous differential equation is one that doesn't mention the independent variable, the thing that you're doing the derivative with respect to. Okay, so it doesn't mention the independent variable. So if you've got, like, for example, dy and dt, and there are no t's, then that's an autonomous differential equation. And your isoclines and nullclines go with autonomous differential equations. And there are two different situations in which they turned up in these notes. And one of them is a lot more confusing than the other one. So as an example, no, not an example, just a second. And the isoclines and nullclines actually aren't just for traditional autonomous differential equations. It's when you've got two of them with different outcome variables. So two DEs with different So, for example, you know, dy on dt is like x plus y squared, and dx on dt is like minus y, or something like that. Okay, these are autonomous because they don't mention the independent variable, and they're linked. There's a word there. They're a system of DEs because they each mention the other variable, and we've got two different variables. Both x and y are both functions of time, but time isn't mentioned here. So just as my picture, that's something like that. That's the story of what we're going on here. And this is the situation in which nullclines happen. Okay. Wait, just give me a second. Okay. So what this means is that for every choice of x and y, there is a way of figuring out what the rate of change of y is with respect to time, and separately what the rate of change of x is with respect to time using the individual point that I've got. So if I've got x and y here, and I had, for example, the point 0.1, let's do a better point, 1, 2. So at the point 1, 2, dy on dt is 1 plus 2 squared, which is 5, and dx on dt is minus y, which is minus 2. So that's what that says. And what that means is that the rate of change of the value of y is 5, and the rate of change of the value of x is 2. So if we think about it as a vector with a speed, it's kind of going 5 minus 2 in the x and 5 in the y. It's going that fast. So this is the minus 2 here, and this is the 5 there. And at every point, you should be able to draw an arrow to say what the speed is of this point. Okay. I don't know what that means, but that's okay. And so if you had a specific point that you were starting at, you could follow that arrow a little bit and then follow a little bit and then follow a little bit, and you would cause a path that you would travel. And that path is called a trajectory. So if you follow you'll get a trajectory, which is a path to follow, right? That's the idea. So the interesting thing about this is that it's like the first 10 pages of the notes, and this is not what any of your other differential equations look like in the whole rest of the course. So it was a weird thing to start with, but you know, that's fine. But that's what it is. And this is a very multivariable calculus thing. So if you do vector calculus in semester 2, then these ideas may come up again. So it's a path to follow. And the path to follow is just saying what the X and the Y are doing. And theoretically, you can we don't have any information about time here, so we don't know how quickly it follows that path, but we do know that it does in fact follow that path. So the first thing I'm going to do is not nullclines, but just trajectories, and then I'll get the nullclines in a second. So in a trajectory, in this case, we've got dy on dt is x plus y squared, and dx on dt is minus y, which means that dy on dx, which is dy on dt divided by dx on dt, because the on dt's cancel, is this. And this is a perfectly good differential equation in x and y now, and there's no t's at all. And this is something that you could theoretically solve with whatever methods you have for solving differential equations. And this would be a curve that involves that is a part that is traced in the x and y graph. So when they say, what is the differential equation that defines the trajectories, that's it. But usually what you'd do is you'd write it in differential form and put like that. And then you'd put them all on one side. And if you were super lucky, this would be an exact DE and you'd be able to solve it. No, it is. That's cool. We are lucky today, but that's a whole separate topic. I'm not going to deal with that. But there are methods for solving this, for figuring it out. But if someone says, what's the differential equation that describes the trajectory? That's it there. If someone says, what is the trajectory? You're going to have to solve this to get an equation with x and y in it, unfortunately. Yeah, so that's sad. How are we feeling? Awesome. I'm going to try and do that about every 5 minutes. Yeah. So the nullclines, we have to go back to our original equations. Bear with me. I know what a nullcline is, but I always forget what an isocline is. This thing produces isoclines. Yes. Yep. Just a matter of setting stuff to zero. Correct. I am going to say that. This thing is the thing that produces isoclines. The original equations is the thing that produces nullclines. So people asked about isoclines and nullclines. They're both here. So we can from here, so this is, this will go, solve the DE, and that will give you the trajectory. But by a separate path, you can get isoclines. And isoclines happen if you find all the points x, y that have the same answer for dy on dx. That's an isocline. So isoclines are x, y's the same answer for dy on dx. So there's going to be a whole lot of x's and y's that produce 0 for the derivative, and all of those together are an isocline. And there's going to be a whole lot that produce 3 for the derivative, and all of those together are an isocline. And there's going to be a whole lot of points that produce, I don't know, minus a half for the derivative, and all those together are an isocline. And that's what isoclines are. They are collect together points that have the same answer for the derivative. And so I'm just going to use someone else's book here. It's ridiculous. So with this one, I could say that, x squared plus, not x squared, x plus y squared on minus y equals 0 would be x plus y squared equals 0. So x equals minus y squared, and so that would be that. So this is the isocline of all of the points where dy and dx comes out to 0. But if I wanted it to come out to 1, that'd be a whole other thing. I have to graph that. Oh, cool. And I just do that one in a different color. So minus y, so 0. So this one is where dy on dx comes out to 1. And every answer that you choose for this will give you a different curve. They'll all give you a different curve. And those curves are the isoclines. That's what isoclines are. So, stepping back, technically, to make isoclines, you don't need the t originally. That's not important. Isoclines can be made from a differential equation connecting x and y. You don't need the t originally. You just need to dy on dx equals something. And then you can make isoclines from that. That's what they are. I don't know why we care, but that's what they are. A nullcline doesn't belong to this. Nullclines come from the original differential equation. They come from here. They come from the one with the t's.
Okay.
Yep.
First reason, or one at a time. So like we had here, you get two equations relating y to t and x to c. And then why are you setting the y dash equal to 0 and x dash equal to 0? What's the focus?
That's what I was about to say. So always slightly ahead of me there. So nullclines are when these things are 0. And null meaning 0, incline meaning incline, so derivative. These things are when the nullclines happen when the two separate derivatives are 0. And they are places where the speed is 0 in the two different directions. So if you have a trajectory that passes across a nullcline, I'm just going to write these down. This is y, x equals minus y squared. And this is just y equals 0. So I have two nullclines. So I'll make this one green and this one, yeah.
What? On page 9, they say nullcline is just a specific isocline. So yeah,
Where do they say that? Oh, yeah.
page 9, just above example 6.
Oh, for the sake of all that is holy. Because they use nullcline in two different ways. Yay for them and for us. So this gray one is the nullcline for this differential equation here. But these differential equations will have two nullclines. And technically, if I think about it, the way they've used the words, there could be a whole set of isoclines for dy and dt and a whole different set of isoclines for dx and dt. But in this course, they've only ever asked you to find nullclines in this situation, and not isoclines. I'm not surprised that we're all confused about this. And hopefully next year's student, too late for you guys, hopefully next year's students will have a better version of this. But in this situation, when they want nullclines, they want the individual derivatives being zero.
So when they also ask for nullclines, we use the derivatives with respect to
Yeah,
time.
so, well, if they said nullclines in this situation, you would just make the derivative zero. So nullcline is whatever derivatives you've got handy, make them zero, and that they are the nullclines. That's what I'm working on at this point. So this blue one is x equals minus y squared, which is this. And this green one is y equals 0, which is this. So they are the two separate nullclines for this system of differential equations. This is the nullcline that makes dy on dt 0. And this is the nullcline that makes dx on dt 0. So the reason we care about those things is that if we had a trajectory, if we had a point, not a trajectory, if we had a point that was here, its x speed is 0, so it's only going to move up or down. Because it doesn't move in the x direction here because that derivative is 0. And this point here, its y speed is 0, so it's only going to move sideways. So if you have a trajectory that passes through this point, it's going to go that way. But a trajectory passing through this point is going to go that way. And at this point here, its x speed is 0 and its y speed is 0. So if you happen to be at that point, you won't move at all. You won't move vertically because it's on the y nullcline, and you won't move horizontally because it's on the x nullcline, so you won't move at all. And this is called a critical point, probably. Is that right? Equilibrium point. Sorry, wrong word. Yep.
Does that mean someone on a trajectory to go to that point? Would it ever reach it, or just slow infinitely towards that point?
I'm going to repeat that. If you're heading towards this, can you get there? And I think the answer is no, you would just slow down. And you would get slower and slower as you got closer to that point. Yep. Yeah, at this point, you can get there because you're allowed to pass it vertically. Yeah. So yeah, and back in Maths 1B, when you drew phase lines, and they had these critical points, and there were like arrows on them, that happened then as well. Technically, on a phase line, you would get closer and closer to the critical point, but you'd never actually quite get there because you slow down as you get closer to it. So, yeah. Okay, so that's an equilibrium point there. Because it doesn't move in the y direction and it doesn't move in the x direction. So all of these points will only move up or down. All of these points will only move sideways, and this one won't move either way. And that's why we want them. And in general, a trajectory will drift towards an equilibrium point because of that whole slowing down when you get nearby. Yeah. So you maybe come past here and I don't know. So generally, in the same way as phase lines, you ended up going towards the nearest equilibrium point. It's usually true that you end up near an equilibrium point if you follow it. And guys, I'd prefer not to have conversations like that or at all while I'm trying to do this. Thank you. Okay. I think that's all I have on that. I'm not going to tell you how to make MATLAB plot them. It's not my job. And you're not going to be making MATLAB plot them in an exam. Yeah. So interestingly, this one here happened to also be one of the isoclines for this differential equation. That'll usually happen. It'll be the numerator. So, yeah. But all I'm saying is that you can make this without starting with the t's. You can make these without starting with the t's. Yeah. I really have a need to draw this one in blue as well. Okay, feel better now. This one's in blue and this one's in green. Okay. As long as I remember to scan it in color, it'll be okay. Okay. Are we feeling all right about that? I wish I understood more about the whys and why we cares, but I can do it. Yeah. So I will say one last thing, that in the notes, they pulled a dodgy and they created this situation of an autonomous DE, system of DEs from a single differential equation, from a second order differential equation. And that was puzzling. So just a super puzzling thing that they did is that they went, oh, I've got do I want to do that? No, I don't. Oh, I'll do that one. So we had an autonomous second order differential equation. And now you actually, theoretically, you could just, no, you couldn't actually. I mean, you could try to do this by separableness, but it's a second order differential equation, which makes it a little harder. And so what the lecturers did, whoever wrote this book, they did something like this. They went, all right, I'm going to let y1 be y and y2 be y dashed. And then they went, well, what that means is that y1 dashed is just y1 dash is just whatever y dashed is.
One.
Yep, which is y2. Thank you. And then y2 dashed is y double dashed. And what that means is that you can sub that we now have an equation that says y1 dashed is y2. Wait. I can now sub these two into the original differential equation and get y2 dashed where the y double dash was and y1 where the y was. And now I have, in combination, y1 dashed is y2 and y2 dashed is y1 squared minus y1. And now we have two differential equations that don't mention their independent variable, which I'm assuming is time, and have two different outcome variables. And so this is now autonomous system of DEs. And so you can draw your isoclines with this thing and draw y1 here and y2 here and pretend that y1 and y2 weren't, that y2 wasn't y1 dashed, and just pretend that it's x and y and just draw them as isoclines as if I was doing it normally. And so you can go like y1. It totally is, because I should have moved them over this side to make them minus. Yes. Thank you. I did ask people to do that, so that's great. Yeah, and so I'll get isoclines. Y1 dashed equals 0 means that Y2 is 0, which is this line. And Y2 dashed equals 0 means that minus Y1 squared plus Y1 is 0, which will be 2 lines. Like that. And so I get this green line is the nullcline for Y1. And this, sorry, yep, that's right. And this 2 green blue lines together are the nullcline for Y2. And so I get 2 equilibrium points just here. And so what that's telling me is if I start, and so these ones are the ones for Y2, which is saying that I'll move this way if I'm on these points, because the Y2 doesn't change, and this one is this way, and you won't move if you're at these points here. But the problem is that Y2 is actually the derivative of Y1, so it's actually difficult to interpret what the hell this means. Yeah. But it does tell me 2 equilibrium points for Y1, which is the original Y. I don't know why that we could have just drawn a phase line for this, but anyway, that's fine. So I end up with these 2 equilibrium points, and the Y1 will drift towards 0 or 1 in this story. And so it's a very clever and therefore slightly confusing thing, but I wanted to say that it was there, that you can create a new set of differential equations and pretend that your Y and your Y dashed are your X and Y, and then you can try and imagine what that means. So at this point, Y1 is like 1 and Y2 is 2, which means that Y is 1 and Y dashed is 2. Yeah. I don't know. The goal is to try and figure out what your variable does when you move time in the original thing here. And so if you can trace a path in here that does whatever it does, then that means that you can trace a path here to see what Y does as time moves forwards. And that's the idea. Okay. Yeah. I don't like it. I mean, it's definitely don't like it as the first thing that happened in this course. Yeah. Again, I can do it, but what this means is that Y will head towards 0 and 1 because that's where because this is Y as t goes to infinity. That's what I would expect. I mean, there may be equilibrium points in the wrong direction. They may point outwards, but I would have to figure that out. Okay. Can I make myself like it more? Well, I guess if you do this, there'll always be, if you do this system, one of the equations is always Y1 dash equals Y2. Always, if you start with something like this. And so your equilibrium points will always be on the Y1 axis. That makes me feel a little better because that makes it like a phase line. Okay, that's better enough for me. But I want to stop talking about it now if that's okay. Is that all right? Okay. But I will happily talk about it longer if you come to the Maths Learning Center. That's okay as well. All right. So we're going to have to choose between the other things on the list. It was a whole year ago, so I can't remember what I did last year. So I often choose things based on things I haven't got a video of.
Last year's video up until.
Yes. All previous years' videos are up on the Maths Learning Center website. Do I tack Fourier transforms?
Yes, please.
Okay. All right. Okay. So the first thing I want to say about this to orient my thinking on it is that the point of transforms is to turn, in this course, is to turn differential equations into algebra equations. Like, and the point of transforms is basically to create a thing that will turn your function into a function of something else in such a way that derivatives here, are something easier than derivatives here. That's my understanding of what they're for. So your classic is Laplace transforms, which we spent a lot more time on than Fourier transforms in this course. So Laplace transforms, you turn like f of t into capital F of s, and f dashed of t here is s times capital F of s here, minus little f of 0. Right? I think that's the rule. Is that right? And so especially if you've got f of 0 is 0, that's particularly nice. And so differentiating here is multiplying by s here, which is way easier than differentiating. And so if you can turn to calculus here into algebra here, then we'll be good. And so the goal for me to make sense of Fourier transforms is to know what differentiating does after I've done the transform. So that's the hope. And in particular, you can't differentiate a function that you don't know what it is, but you can multiply a function that you don't know what it is by s, because I can just write s next to it. And I know what multiplying an unknown function by s does algebraically. So I can solve problems that have multiplying by s, but it's much harder to solve problems that have differentiating a thing that I don't know. That's why. So I'm going to now look up what the rule is for Laplace transform, for Fourier transforms, and then I'll go back and figure out what they actually are. But this is the most useful thing I want to know. And I will look up in the contents. Fourier transforms, page 150. For the purposes of copyright in the video, this book is produced by the School of Mathematical Sciences at the University of Adelaide. I did not write it. Okay. Funny thing to me is that actually it's not called the School of Mathematical Sciences, it's the School of Computer and Mathematical Sciences now. So this is older than 2022.
Are they going to make a new one for next year?
I would imagine they would at least write Adelaide University on it. There are mathematicians who do differential equations at UniSA as well, so presumably they're trying to meld it together into one new course. But also engineering, the associations that give accreditation to engineering degrees have specific requests on what should be in differential equations courses. And so across different universities, they're not that different in Australia. Yeah. Sometimes I wonder why those accreditation bodies request certain things in differential equations courses. And sometimes I think it's just a rite of passage. Well, I did it when I was your age. So anyway, moving on. Okay, Fourier transforms. Here we go. Oh, Fourier transforms are complex number things. What? Oh, no, there's more than one kind. You see, I only do this once a year. Maths 1B I do 3 times a year, so I can do that off the top of my head. But that's the plus transforms. Oh. Bear with me. I'm just looking at this. Okay, the Fourier transform is a complex number thing, but you can back form it into a real number thing if you really concentrate. Okay. But the classic Fourier transform does this. So Fourier transform, we have f of x this time becomes f hat of w and f dashed of x becomes I times w times f hat of w. Okay. Right, fine. That's sure. And why not? So it's quite similar. Let's just look at the similarities here. We do still multiply by the variable that's on the inside here. It's just that the Fourier ones has a bit of extra spice with this I here. Okay, and I think that this is the goal of Fourier transforms. It's still the same goal. It allows you to turn a differential equation involving x that dx's into a new differential equation, into a equation that doesn't have any f dashes, because f dashed here becomes straight up f hat here. So you should be able to do algebra, admittedly with complex numbers, but we'll be fine to get what you want to get. Okay, this feels to me like the important thing to remember. Now, interestingly, the Laplace transform came with a whole table of what things become, but the Fourier transform didn't. It did. Like it didn't have as big a table though, right? This. See, look at this. The Laplace transforms, right, have a table of theorems, right? And a table of this function on this side becomes this function on this side, right? Whereas the Fourier transform just has a table of theorems. It doesn't have a what functions become what functions, which is weird to me. But anyway, I just think that's weird. And that's why they're more confusing, because you haven't got a list of what to do with things. You have to do the integrals every time. So there's a definition, and the definition according to said formulas is that if you have f of x, then when you do the Fourier transform, which is called traditionally f hat of w, then it is 1 over root 2 pi of the integral from minus infinity to infinity of f of x e to the minus I wx dx. Okay. This is also known as curly f of curly brackets little f. Sure. And you can come back the other way as well. So if you have f dash hat of w and you want to come back to f of x, then this will be exactly the same integral, but with a plus I and a dw. These are listed on a sheet that comes with the exam, but it's useful to have them. Yep.
So that some functions when they approach infinity and negative.
I shall repeat that. Surely some functions, when you approach negative infinity or plus infinity, there's no answer. So wouldn't that mean that some of these don't exist? Yes. I presume that there are some functions that the Fourier transform will not give you anything useful of. Ah, well. So that we can do this. Yep. Yep, so the derivatives become algebra. So differentiating becomes multiplying by W and multiplying by I. And what that means is if you have an equation that's got derivatives in it, then you can turn it into an equation that's got algebra in it. Yes, we will. Let's do it. No, let's put this back in the page that it was in. Don't want to ruin your system. Okay. Okay. So bear with me. I'm just going to give something a go. It may turn to crap, but I just want to try it. One of the ways to try understand things is to give them a go and see what happens. I mean, do we have the safety to do that now? Like a week and a bit before the exam. Really? Oh gosh, it's so close. We have the safety to do that now, when we're not during an exam, to just give something a go to see how it works. So if I had something like this, right? It's a perfectly good second order differential equation. And we actually have methods for solving this already, so I know what the answer is going to come out to if I concentrate. And my x is going to be no restrictions on x. I want to see what happens if I Fourier transform it. So I'm going to say that the Fourier transform of y of x is going to be y hat of w. That's what I'm going to do. And what that means is that the Fourier transform of y dashed would be iw times y hat w. And the Fourier transform of y double dashed would be doing that twice. And that's minus w squared. I have no idea if this is useful, but I'm just thinking about what this means for me, this derivative thing. And so what that means is my original differential equation becomes minus w squared y hat plus y hat equals 0. And so I get that that's not helpful at all, but that's okay. Okay. I feel like I've done something wrong. I feel like maybe that 0 there. No, because if I Fourier transform a 0, there'll be a 0 in that spot, and the integral of 0 is always 0. Damn it. I really thought that would have helped. Okay, but it's certainly algebra now. It was, yes. I just wanted to do it on the not partial one to make me feel better. But I can do the partial one as well. So if this hadn't been a 0 and had been something else, then maybe we could have done it and it would have turned into something nice here. But then, not that I know how to un-Fourier transform like 1 over 1 minus w squared, I guess.
Is it? No.
Yeah, I don't think so. Yeah, no, you'd need a table that told you what things involving W become things involving X, which we don't have. All right, that was a bad plan. Sorry. So it must be, they must have done this after the PDEs bit, because PDEs is when they're useful. I will say another comparison that's useful here is that this integral goes from minus infinity to plus infinity, and the integral that is officially the Laplace transform only goes from 0 to infinity. And so the Fourier transform is able to cope with things where the variable can be negative. Whereas in Fourier transforms, it's only, the reason it's t for time is that t always starts at 0. And it only talks about time onwards from now. So Laplace transforms start at t equals 0, but Fourier transforms are able to deal with the x being negative. Okay. Well, now I'm really interested in seeing what the hell's going on here. So that's a Laplace transform. And the Fourier transform was with a PDE, was it? Oh, actually, there is, just a second. So this is their example. I'm just interested to see what I'm just going to pick a number. I feel like I should pick a square number. Okay. And the x is from minus infinity to infinity. Yep. Okay. And they've given us that rho x0 is delta x, and rho x0 approaches 0 as x goes to plus or minus infinity. That's the one that they've given us in the notes. I have actually translated the notes. They've talked about this equals f of x here, and then they said that f of x is delta x, and I've just, maybe there should be a t here. I think that might be true. Nope, they've just done this, so we don't need that at all. Okay. Oh, so look at that. Let me wait. Yeah, that's so cool. So look at this thing here. They've said that this is only going to work if your function goes to 0 as x goes to plus or minus infinity. And that's because that means that when you do this integral from minus infinity to plus infinity, that means that when you get close to go to infinity, this bit becomes 0. And so that means that it's only going to turn out to just have, it's going to work. Okay, right. So you have to have a function that will go to, you have to have a function that will go to 0 when it goes to minus infinity or plus infinity. Or at least for this one, technically, probably you only need it to go to 0 when x goes to minus infinity, because the minus here will make it go to 0 on that side. So, okay, I understand a bit better about that. So, yeah, your question of doesn't always work is no, it doesn't, but they'll give you situations where it will work. Okay. So if you look really closely at things, you can learn stuff that you didn't expect to learn. And so then they Fourier transformed this. So they went P x t is going to become P hat w t via the Fourier transform. Okay. And so we're going to Fourier transform every piece of this. So dp on dt will become, I guess, dp hat on dt, because that's fine. and the d squared p on dx squared will become p hat times IW for the first derivative and times IW for the second derivative. And so I'll get minus W squared times p hat. Yep.
Why is it the same?
Well, technically this has got an xt in it, and this will become a wt. But because this is differentiating with respect to t, and the t isn't being changed in this process, the derivative with respect to t won't change either. That's why. But this process only changes the x's to w's. And so because the t is still a t, the derivative with respect to t will still be a derivative with respect to t. Okay, and so my differential equation the dp on dt becomes dp hat on dt. 25 still 25, and this becomes minus w squared p hat. And lo and behold, this doesn't, this is now a differential equation with one variable, not two. We used to have a dp's, dt's and dx's, and now we just have dt's. And so we're going to pretend for a minute that this is a straight dt as opposed to a curly dt, and solve this as if it was that thing. So I know the differential equations are the only functions that are equal to a multiple of their derivative is e to the power of stuff. And so this is telling me that p hat is therefore e to the power of minus 25w squared t. Time's a constant, right? I've skipped working there, but you have done this so often in this course, you should be allowed to just write that down. Yeah, the only functions that are a multiple of their derivative are e to the power of something times thing. You're allowed to just write that down. Unless they explicitly say, solve this differential equation, like not as part of some other working, but just on its own, then maybe do separable differential equations. But this can just be done that way.
So we can solve it just using subtraction of the level that we do. We don't care about each other. I agree with that.
No, we're just going to pretend they're there. The only point at which we are going to care is that this constant may not be constant. It may be a function of w. So when you solve a solve a differential equation that is a partial dE but doesn't have, it's only got one variable, then all the constants that appeared along that process aren't constants really, they're functions of the other variable. And the reason is that when you differentiate a constant, it goes to zero. If you differentiate just curly dt, and something that has w in it counts as a constant. And so it would have disappeared. So that's the shortcut version. So this would be normally just a, right? But because it was a dt, it will be a of w. That's why. See, in the course, they literally just went from here to here. And that's because they're expecting you to just know how to do a differential equation that works like that. So I'm just going to write on the side here, if I had y dashed equals number times y, then that would mean that y is e to the mt, something like that. That's the rule I'm using just here. And now I have to Fourier transform that, because my goal is to figure out what the original p was, and the original p was in terms of x. So I need to turn all my w's into x's. But I could also So you have to get that back to x's. Or I could be very careful and transform this as well. That would be good too. And sub that in now. So this was me figuring out what the transform did. Ah, because you do that when you do Laplace transforms, don't you? You transform the initial conditions as well, don't you? No? Laplace transforms for PDEs. Yeah, okay. All right, that's fine. So I'm going to transform this to px0 will become p hat w0, but this is equal to delta x, which means this would be equal to, and this is the first time that I have no choice but to just do the integral. 1 on root 2 pi, the integral from minus pi to minus infinity to infinity of delta x e to the minus iwx dx. I know it's dx and not dw because I have to be left with w's at the end. And if it was dw, I'd sub in numbers for the w's and they'd be gone. So, but if I sub in numbers for the x's, then it'll make the x's go away. Okay. Well, when you integrate delta x from minus infinity to infinity, you get 1. Because delta x is mostly 0. Yeah, delta x is mostly 0. So this would be totally the same as integrating whatever the answer to this is at 1. So this should be, so at 0, sorry. This should just be e to the minus iw times 0. I think I'm right about that. I really should just read the solution instead of making up crap, but nope, that's right. So when you integrate anything multiplied by delta x from minus infinity to infinity, you just get what you get when you sub 0 into this. Because delta x is 0 everywhere except where x is 0. Yeah.
So if it was x minus a, I would just put
A in, yeah. That is one of the major features of delta x, that when you integrate it times another thing, it just subs in the number into there. And so this is literally just 1 on 2 pi. Okay. So back here, okay. So p hat of xt was aw e to the minus 25w squared t. And so p hat of x0 will be aw e to the minus 25w squared times 0. But it's also supposed to be 1 on root 2 pi. And so therefore aw is just the number 1 on root 2 pi. Okay. Cool. Oh yeah. Thank you. And so therefore our equation is now that p hat is 1 on root 2 pi e to the minus 25w squared t. And I'm going to have to Fourier transform that. Okay. They convoluted things. That's okay. I can see why they've done it the way they've done it. I did not do a good job of this, and I'm very sorry. Thank you for bearing with me. So yeah, the P should be the inverse Fourier transform of this. But I'm not a fan of this inverse Fourier transform, because that's also an integral of something I don't like. Okay. If I were in an exam at this point, I'd go, well, find marks where you can, and I'd move on. But if I was in an exam at this point, they'd probably have given me some hints, because this is the last thing in the course. Yeah. I'm just going to see what they did. So this is the point where I was. That's the Fourier transform of the initial condition. That's where I am here. And that's the Fourier transform of the original function, which was delta. So that's the point. I am at the same place here that they were on the previous page. Okay. Mm. Oh, I see. Oh, apparently in tutorial 11, we found the inverse Laplace transform of e to the minus something t, of e to the minus something times w squared. So, okay. So we're just going to add this to our list of functions. This is the only function that they have given us an answer for. We know what the Fourier transform of delta x is. It's 1 on 2 pi. And in tutorial 11, apparently, they found that the Fourier transform of e to the minus dw squared is apparently that. Okay. Let's put the VT as a C. There you go. That's apparently in tutorial 11. So if you're in an exam and they're going to get you to use that, they'll just tell you, I reckon. They'll say, hint, the inverse Laplace transform of this thing is this. And you go, okay, cool. And so therefore, this is apparently in tut 11, therefore, if p hat is 1 on root 2 pi is that, then P must be the inverse Laplace transform of this. So the 1 on root 2 pi will still be there. And this will become 1 on root 25t e to the minus x squared on 25t. Because this 25t is playing the role that c plays here. But there's be a 4 there, 100. Yay. I am not edified by this. Feels like an afterthought, the end of the course. We've got a lecture to fill. Let's just squeeze this in here. Okay. I mean, compared to Laplace transforms, which are some deep, cool cleverness, I'm not impressed. Sorry, Fourier. Just pales in comparison to Laplace. Sorry, dude. Don't like it. I do notice that there was some really pulled nice Swifty by giving you a differential equation that doesn't end up involving I when you do the derivative because you did a second derivative. So it seems like Fourier transforms are really useful for second derivatives because then you don't get annoying I's floating around. So if they got you to do this, I reckon they would have given you some of these bits of information like this one. And they would definitely give you something where the I wouldn't appear. I don't want to talk about that anymore. Is that okay? So if I was going to pick one last thing to do in the last 10, possibly 20 minutes, what would I do? I mean, I can talk about Laplace transforms while I'm on the transform train. Yeah, yep.
This would be fun.
Okay.
The pretty good in not really within line sums, but it looks open and looking for the just the conversion from the Fourier series into the transform I didn't entirely follow.
Ah, gotcha. This thing?
Oh, yeah, fine.
So this is the real one where we have a Fourier cos and a Fourier sine transform.
I mean, to understand the sort of derivation of conversion.
Possibly. Give me a sec. Okay, so there's two pieces here. There's the original Riemann sum weirdness for moving from a Fourier series to a Fourier transform. Oh, I see. Okay, just a second. I said earlier that we don't say things are stupid, or ourselves in particular. So you're charged to say two nice things about yourself later. So a Fourier series is a way of writing your function as a sum of sines and coses. As opposed to a Taylor series, which writes it as combinations of one x squared, x cubed, x whatever. So a Taylor series, you go f of x is, something plus something x plus something x squared plus and so on. That's how Taylor series works. And then you figure out what these terms are by doing derivatives. That's how Taylor series works. A Fourier series, you write f of x as a combination of causes a2 cos 2x and a3 cos 3x and so on, and sines. Sine x, b2 sine 2x, b3 sine 3x. That's a Fourier series. And you, instead of using derivatives to figure out what these numbers are, you use integrals. And this a0, that's technically cos of 0x, because cos of 0 is 1. So a0 times 1, technically. So instead of figuring out these coefficients from derivatives, you figure them out from integrals, because it's not the derivatives of sine and cos that are helpful, because they just turn them into other coses and sines. It's the integrals. And so you figure out what a2 is, for example, by integrating your original function times cos of 2x across the entire domain of cos, like the one whole period of cos, and then you divide by a magic number to make it work out. And this is the number you would get if you put cos 2x in that spot. So yeah, and the b2 would be the same but with a sign, and the a0 is and it's 2 pi this time, I believe.
Separate.
Yes. So one of the reasons they taught you Fourier series is so that you can do PDEs. So when you do a PDE, you get this answer. It's got a whole lot of sums and it's got sines and coses in it. And usually when you sub in one of them, the t equals 0 or something, you get something that involves only causes. And so that's technically a Fourier series. And so you can match up the coefficients of cos on one side to the coefficients of cos on the other. So one of the things about Fourier series is that every function's only got one Fourier series. So here's the thing. Here's the thing. When you do a Fourier series, you can do it complex number-wise if you want. And instead of using cos and sine, you can use e to the I x, because that includes both the cos and the sine simultaneously. And that's one way of thinking about it. When you do, let's step back. So if you have an even function, so what that means is that your function is the same on both sides, like that. If you have an even function, you can only, it turns out that when you do your Fourier series, you only get causes. And that's because sine is an odd function and it's just not going to be involved when you make an even function. So you end up with your f of x only involves causes or the constant. And this one has period 2 pi, and this one's got period pi, and the next one's got period 2 pi divided by 3. This one goes twice as fast as cos, and so it has more peaks and troughs in each zone. But it still repeats itself every 2 pi, it just repeats itself even more often than that. So this is great. And so here's the thing. I know that the various numbers that go in these spots, that an is going to be 1 on pi, the integral from minus pi to pi of f of x cos of nx dx. And this will give me the coefficient, but there's no particular reason why I shouldn't use a number that isn't a whole number. Like I know that here I have to use a whole number, obviously, but what if What if I just did this integral for n equals like 2/3 or something? I could totally do it, right? Be 100% a thing that I could do. That is now a Fourier transform. This is like a function, right? That gives you a different answer for every n. Well, I can make a function that gives me a different answer. I can just put W in that spot. That's what the idea, one of the ideas behind what the Fourier transform is trying to do. But instead of going from minus pi to pi, we do it from minus infinity to infinity, because my function might not actually be periodic. So maybe my function doesn't repeat itself every 2 pi. Maybe it repeats itself every 10,000. Or maybe it never repeats itself, and so I kind of go, oh, cool, the period is infinity. And so I'll go from minus infinity to infinity. I won't divide by infinity because that's ridiculous. But anyway, don't get me started on the stupidity of some of these things. Like, but the whole course is like this. Like the entire of this course is like, okay, some person in the past went, I wonder if I could solve a differential equation by doing this trick. Cool, I can. Can't do these ones, but these ones I can do. And it's similar idea. It's like, oh, what would happen if I did this? Would that help? Apparently, sometimes yes. Yeah. So that's how it tells me about things. And if, like, yeah, anyway. If it turns out that mostly your coefficients, like these things, are mostly 0, then it turns out to just be a periodic function. And so Fourier transforms technically are, if when you do the Fourier transform you get a function that is mostly 0, then that tells you your original function was periodic. And so that's kind of the idea behind it. You say, well, why don't I do this integral for all possible values of n, including the non-whole number n's, and see what happens? And maybe it'll turn out that when the only one that isn't 0 is n equals 2/3. And you go, oh, cool. So it must be cos of 2/3 of x. Great. And so my period is what? A weird-ass multiple of pi. I don't know. That's what I'm making up. I'm making up most of these as I say them. I'm saying things that sound reasonable. But sometimes that's all you need to feel better about it. Yeah. So there you go. And Fourier transforms. So everything I've said just there tells you that I too am uncomfortable with this reasoning. Okay, so this e to the minus whatever is a way of doing Fourier series, but using complex numbers to wrap the cosines and sines together into one thing. And then because we've got a sum of things that involve integrals, I could theoretically switch the integrals and the sums and then go, cool. Oh no, that's not how it works at all. I really hoped that was it. Oh, bear with me. Okay, I'm good with this. This is the Fourier series. So we've got e to the I whatevers. And that's what's causing these pairs of coses and sines that match up. That's what this is doing. And each of those has a complex coefficient so that you end up with the right real coefficients when you multiply it out. And then what changed between here and here? The 2L disappeared, right? Yep, so this delta W is in fact L on is in fact pi on L, right? Oh, they've got that there, duh. Okay. Okay. Is pi on L. And then
They pull the 1/12 outside and then split it into.
so just a second. They've gone, L's gone to infinity, so this has gone to infinity, but then this has gone to 0. If L goes to infinity, then these L's definitely become infinities, but this pi on L becomes pi divided by infinity, which is technically 0, but we're not going to do that. We're going to turn this delta W into a dW. That happened when L went to infinity. Okay. And when L goes to infinity, a sum becomes an integral.
But my problem was with that sum was referring to n, not L. So how come the L going to infinity affects the sum?
True. Yep. Don't like it. I don't like it in the same way that you don't like it. But at least I know what each bit became. That's a little easier. Nah, I don't like it. But what I do like is just being a little less precise about it and just waving my hands and going, all right, let's do this. And not worry about some of the details. Yeah, that's fine. I there's so many parts of this course that I'm really good at. And so I'm sure I could pass the exam, and you can do it too. These bits worry you. These bits worry you. But mostly the things that they didn't care to explain, they don't care for you to explain. Yeah. They put it there to make themselves feel like they did their due diligence for giving an explanation. But really, they don't care. If they cared, there would have been a better explanation. So that's I'm sorry to all writers of this thing that I have offended you, but you're not going to watch this anyway. But if you are, hi there. Yeah. So that's fine. I'm okay with that. When I look at the real Fourier transform, it's exactly what I said. I replaced the n with a w. I put some fluffy weirdness here to deal with some of the details that I need it to deal with so that I can get the IW without any pies and stuff. But everything else is fine. Yeah.
Those ones, even Fourier transform either odd or even sum.
Yep. Or you can have a function that starts at 0 and you pretend it's odd because you don't care what happens before 0 anyway, so it might as well be odd. You have a function that only starts at 0 and you just pretend it's even depending on which one you want. Same as when you did not Laplace transforms. Same as when you did Fourier series and you just pretended your function was periodic. You go, oh, well, I don't care what happens outside this zone anyway, so it could be periodic. So whatever. So that's be my plan there, is that you can just go, well, if your function only starts at 0 anyway, then you just pretend it's odd. Or even depending on which one matches up with your PDE that you've got. But yes, officially it says that you can only do the cosine one if it's an even function. Yeah. Oh, look at that. Look at this. If f of x is defined on 0 infinity or minus 0 infinity, we can define either the Fourier cosine or Fourier sine transform by taking an even or odd extension. So that's the official words, even or odd extension, is what I call pretending it's even or odd. Yeah. Yep. Okay. And apparently that helps. But I find that there's not many examples of using them in ways that make sense to me. I would much prefer that they didn't do the complex one and just did the real one, because I'd feel better about that. But there we go. So what I'm going to hold on to, if I was going to go into the exam with Fourier transforms, is this fact here. Because that was the thing that was useful for the examples that we did. And I'm going to hold on to that there are a small number of functions, i.e. 2, that we know how to un-Fourier transform them, and they are these. This one, I don't know whether that's going to come back in your exam, but I have a feeling that they'll just write it down. And delta x, which I can always derive straight up. Yeah, the Fourier transform of delta x is 1 on root 2 pi. So that's the best one I can do. And also that any function that they give me that isn't 0 at the two ends isn't going to work. So, yeah. So that's what I'm going to hold on to. I'm going to hold on to it tight. And because everything else, the closer I look at it, the worse it gets. Well, I hope that is not too disappointing. But what you have learned with this, at least, is that if you talk to me about any of these things, I'm going to try my damnedest to get to a point that we understand or at least feel okay about it. So you can trust that if you come and visit me in the Math Learning Center. Those watching this online, it might not be true past 2026, but it is true this year at least. I will be in the Math Learning Center up until the exam. On Monday, I won't, and Tuesday, I will be in revision seminars, mainly. But Wednesday, Thursday, Friday, I'm committed to just being in the Math Learning Center. So totally okay to have a nice little DEs for Engineers enclave there, and I'll come and check on you every so often. So, but the other tutors know about a lot of these things. And they will, give it a good hard crack and at least find someone who knows more if they can't. But I personally will be there if you want to talk to me. But to be fair, everyone wants to talk to me. Yeah. If you do want to find out about any of these things, Laplace transforms and Fourier series and power series, most years I talk about at least one of those things. So if you look at the past revision seminars, if you want to fit more video content into your life, you can at least see what I said about it in the past. And I did talk about a Fourier series in the DE's plane, the other course revision seminar this morning, so you can watch today's. Yep.
Know actually that much about Bessel functions?
I don't think so. I don't think you do need to know. The Bessel functions are the standard solutions to the Bessel's differential equation. And you need to probably know that they came about by doing that. The J's come about by doing, just a second. The J's come about by doing Frobenius's method. And the Y's come about by doing reduction of order. But that's pretty much all you need to know. The important thing is to know what differential equation they answer. So I know the Bessel's equations are like x squared y double dashed plus, and there's other stuff after that, but that's how they begin. And they're a specific differential equation. And then and if you do Frobenius's method, you get some answers, which are power series. And whatever those functions are, they are the Bessel functions. Yeah, so that's all you need to know is what differential equation they satisfy. So if you've got a J, which they're called J, right? J and Y. If you've got a J and a Y with a little nu in them, you can write down immediately that J double dashed x squared J double dash plus blah, blah, blah equals 0. And you'll be able to know that. So officially, damn it. It would be under Frobenius's method, wouldn't it? Bessel's equation and Bessel's function, page 82. So that's Bessel's equation there. It's got x squareds at both ends. And there's this wickedly fun formula for the J, which is a power series. But the important thing to know about J is it satisfies that equation. So if I wrote down J nu x, if that was what y was, then I would know for certain that y double dash x squared y double dashed plus x y dashed plus x squared minus nu squared y is 0. That I know for sure. And so what that means is if they gave me a number, right? If y was j, I don't know, 5x, then I'd have x squared y double dash plus x y dash plus x squared minus 25y is 0. So that means that theoretically I could figure out if someone told me what j dashed was, I could figure out what j double dash was from this information. Yeah. That's pretty much it. There's nothing special about them. And y5 is also satisfies this same differential equation. So yeah, I think that's pretty much it. I don't think there's anything special beyond that. They're just particular functions that happen to satisfy the differential equations you're looking for. And also that j of minus 5 is minus j of 5, like j5. Yeah, that's all. And I guess somewhere later on they said that they're orthogonal to each other. So if you had like j5x, j4x from like 0 to probably infinity, you'll get 0. Yeah. So as long as these two numbers are different, they'll be orthogonal. That integral will come out to 0. Which means you can make Fourier series out of them using them instead of sine and cos, but yeah, don't go there. But there's all these things that they say so that if they appear in one of your later courses or when you're reading a paper, then you don't freak out. And that's one of them. Like, you know, when you do your Fourier, when you do your PDEs and you get sines and causes, sometimes you get Bessel's functions. And so you can, like, they have to be pretty crazy. But sometimes you get Bessel's functions. And so you can say, oh, well, let's just write my left-hand side as a Fourier series with Bessel functions and match them up instead of the sines and causes. That's just crazy talk. Yeah, I don't think, for me, it's just knowing which differential equation they satisfy. That's the important thing. Yeah. So, yeah. And to know what they look like, you know, they're squiggly. And they decay, right? They get, yeah. Yeah. Okay. Oh no, there must be a choice. Just a second. Oh no, okay, no. Ignore that. Yeah. So it's a, I don't know. I guess basically any differential equation that has a name usually has a function that goes with its solutions. And Bessel's equation has a name, so there are Bessel functions to go with its solutions, and that's all there is. That'll do. I'm going to stop now. And I will stop the sharing and stop the recording.